for the signal for streaming. You didn't come from far, right? EPFL,
not too bad.
Not so far.
Not so far, yes.
And you're going back there for Eurocrypt?
I will be going back to Lausanne on Sunday, actually, yes.
Okay. So, as I said, this is a submitted proposal that we're happy to have here on ZKProof 6. Andrew, the floor is yours.
Thank you so much. Great. Let's talk about Sumcheck. Thank you for joining my presentation. The title of my presentation is Blendy, and Blendy describes a space-time trade-off for the Sumcheck prover. This is joint work with Alessandro Chiesa, Elisabetta Fedel, and Giacomo Fenzi. Great. So let's look at some brief motivation. Where do we see Sumcheck? We see this in concrete constructions of ZKVMs and lookup arguments. It's also used in GKR. And most recently, we see this in constructions like Jolt, Lasso, and Gemini. And these constructions aim to reduce prover time. We also want to reduce prover time, and we also want to reduce memory usage as well. Great. So let's do some recap. What is Sumcheck? Sumcheck is an interactive protocol. And what makes Sumcheck special? Well, of course, we can construct interactive protocols without using Sumcheck. But when we use Sumcheck, we are provided the sufficient algebraic structure to arithmetize any Boolean problem into a statement about a low-degree polynomial. Specifically, it allows a prover to convince a verifier about statements of the following form: that the summation of a polynomial over some domain, in this case a Boolean hypercube, sums to some value gamma. OK, great. So let's walk through two cases. The first case, let's walk through a case of a univariate polynomial. And in the second case, let's walk through a case of a multivariate polynomial. So in the case of a univariate polynomial, what happens in this protocol? Well, the prover is going to send this univariate polynomial to the verifier. The verifier is then going to evaluate this polynomial at points 0 and 1. And it's going to sum, and it's going to check if this is equal to gamma. If this is equal to gamma, then the verifier is going to accept, and we are very happy. OK, great. It turns out if we want to adapt this to the multivariate case, we don't need to perform too many different tricks to make this happen. So let's consider the first round of a multivariate case. And it turns out the first round is almost identical. The prover will send a univariate polynomial to the verifier. The verifier will perform the evaluations. It will check if the sum equals to gamma. And if they accept, then in the last step of the first round, they're going to sample a field element, and they're going to send this field element to the prover. What they mean by sending this field element to the prover is that the prover should take this first variable, and they should fix it to this randomly sampled field element. So to speak, as the prover moves forward into next rounds, this first variable is absorbed with the value that the verifier supplied. And we will see how this plays out in the next round. So let's move forward to the second round of the multivariate case that concerns itself with the second variable in the polynomial. So what's going to happen? A very similar thing is going to happen. The prover is going to prepare a univariate polynomial. They're going to send it to the verifier. The verifier is again going to evaluate this univariate polynomial at points 0 and 1. And this time, instead of checking the sum of these values against the value gamma, they're going to take the univariate polynomial from the previous round. They're going to evaluate it at the randomly sampled elements that they provided the prover in the previous round. OK? If this works, then we proceed forward. We sample another field element. We send it to the prover. And we continue in this manner for all of the variables in the polynomial. If all of these checks work out, and we've performed this round interaction for all of the variables, the last thing we do is we're going to perform an oracle check for more or less the random point that we have been generating through all the rounds of the protocol. This is pretty much the complete protocol. It's quite simple and quite powerful. Some basic asymptotics. The verifier here is evaluating a univariate polynomial twice for log n rounds. And if you're curious, the prover is implemented in a naive way, in this sense, would run in quadratic time. So I can stop here if there's any questions. I think this is probably clear. OK, great. So let's look at some techniques. The first technique we're going to look at is log space Sumcheck. So this has nice space complexity. And what's the main idea here? So the main idea here is to leverage the fact that we are representing the polynomial as a set of input-outputs. So we have either a stream or a function, or maybe it's even a list. And if you want the evaluation of the polynomial at 0, 1, 0, you go to this location and you find the evaluation. So the way that I would invite you to think about this technique is, let's say that we find ourselves in a round of the Sumcheck protocol, and we have a polynomial with 8 variables, and we see that we have received 3 random challenges from the verifier. This means that we have completed 3 rounds of the protocol, and that the current round concerns itself with x4, which is the first open variable in this list. When we mentally create these 2 subsets of fixed and open variables, this allows us to see some sort of structure that we can use to make our summation in 2 loops. In the outer loop, we are iterating over a hypercube that is of size equal to the number of fixed variables. And in this loop, we can perform an interpolation. We will talk more about interpolation later, because there are some techniques in certain situations to reduce how many field operations we perform. Great, so what's left in this? There's just to loop over the open variables. We find that we can perform our summation here just by multiplying lag poly by the evaluation of the full point here. And the key takeaway here is just the observation that the lag poly is going to be the same for a lot of these points here. Great, it's a pretty simple technique. And if you look at the code, it's really actually, I think, only 30 lines. Cool, so let's look at another technique. This is linear time Sumcheck. This uses a bit more space, but has attractive time asymptotics. So what is the main idea here? The main idea here is to keep a lookup table. And in each round, we want to compress this lookup table by absorbing randomness from the verifier. Great, so I've listed out here a table, and you can see that since we have a list of evaluations over the Boolean hypercube, the indices that I've listed out here are actually the points, and it's quite convenient if you move from left to right. It's 0, 1, 2, 3, 4, 5, 6, 7. Great, so what did we say we want to do? We said we wanted to absorb verifier randomness, and we want to fold this into a smaller table. So the question we arrive at here is, how do we take this table from round n-1, and how do we fold it into a smaller table found here in round n? Well, the proposal that I'm making is that when we look at all the indices of the table in round n-1, you'll notice that each index has a partner index that has a same suffix. So in this illustration, the indices colored in yellow share the suffix 0, 0. So we can perform a folding defined by this little snippet here. It's very simple. You get one of the values, you multiply it by the verifier randomness, and you add this to the other value multiplied by the verifier randomness hat. It's quite simple, and you can see that we do this for all the colors, and it's compressed into a smaller table. The round evaluation in this technique is also very simple. You basically have 2 sums, and you will loop through your table in round n, and the odd indices will get summed into one sum, and the even indices will get summed into another sum. Again, it's pretty simple and quite nice and works well. Is there any questions? Great. Sure.
seconds back.
Oh, yeah, sorry. I think I got a bit lost on the trade-off. So what is that you win and you lose when you use this approach in compared to the other one?
Yes, so in this log space approach, you're using log n space because you're not keeping that table that you reduce over the rounds. So if you look at this, I can add the pseudocode in there for you. You're not using any data structure, you're just looping over all the variables. But you notice when you've received randomness from the verifier for all of the variables, you're going to have to perform your lag poly over log n elements because they'll be,
Yeah, sorry.
Yeah.
Perfect. Thank you.
Okay, great. Thanks. Great. Yes. So just to recap that question, there's this trade-off of space and time between linear time Sumcheck and log space Sumcheck. Great, and that's kind of the point of Blendy, so cool. We present Blendy, which is a multilinear Sumcheck prover with the following asymptotics. You can regulate this trade-off with this constant k. If we set constant k to 1, this recovers the asymptotics of linear time Sumcheck. And if you set it to n, you recover the asymptotics of log space Sumcheck. You can set this to different values of k, and you discover other trade-offs that were previously unknown. Great. So we've implemented this in Rust. You can find it. Oops. Sorry about that. Spoilers. You can find it on GitHub here. We use the ArcWorks ecosystem for field arithmetic. We've implemented Blendy, and we've also implemented log space Sumcheck and linear time Sumcheck. You can look at the code. You can choose different fields. You can modularly choose your prover algorithm, and you can even supply different input streams if you want to read from disk or do something crazy. Great. Let's look at some concrete results. So we performed some tests on a large machine, and we find that compared to linear time Sumcheck, Blendy uses significantly lower memory. Also, compared to log space Sumcheck, Blendy runs orders of magnitudes faster. So if we look at a specific example, such as an input with 28 variables, we see that Blendy has a 650 times improvement in memory usage, and this is traded for a moderate slowdown. Questions? Great. OK, so let's look at some techniques. So the main idea we have here is that we want to divide the rounds of our protocol into stages. Again, stages, the number of stages is defined by k. And as we go forward, remember that we want to incorporate techniques from both log space Sumcheck and also linear time Sumcheck. So what's a technique that we use in log space Sumcheck? Well, we had that mental making of subsets of the input variables to our polynomial. So in log space Sumcheck, we had two subsets. We had the subset of fixed variables, and we had a subset of free variables. Since we have a little bit of added complexity with these stages, we're going to actually suggest having three subsets here. So there's the subset of past variables, which correspond to variables that were handled in previous stages of the protocol. We have the subset of current variables, which concerns variables in the current stage, and then we have future variables. Cool, so what does this allow us to do? Well, it gives us a place that we can perform our interpolation function. So we can perform interpolation over past variables, since we know that we have the randomness for all of these variables. Great, and at this point, we can incorporate a technique for linear time Sumcheck, which is we want to compress into a lookup table. It's really a straightforward pull from both of these techniques. You can see that we are compressing using this folding operation into a table that is of stage size. Any questions? I think this is pretty straightforward. Great. Let's move on, and we just need more or less one technique, and then we can do our round evaluation in this algorithm. So what is the technique? We call it partial sums, and I'm going to describe how we do it, and then in the second half of the slide, I will explain how it's used in the round evaluation. So what do? We want to create a new table. We're calling this partial sums, or PS, and how we fill in this table is as follows. We take the aux lookup that was generated in the previous slide, in slide 13, And at every index of PS, we want to fill in the index with the corresponding index of ox, and also every value that occurred before that index. So if we read from left to right, in the 0th index of PS here, we place the value of ox at 0. In the next index of PS, index 1, we're going to place 2 values from ox, ox1 and ox0. And in the second index, the next index of PS, we're going to place 3 values from ox, ox2, ox1, ox0, and so on. And we move forward. OK. So why did we do this? We've arrived at the round evaluation. And you can see here that for 0 and 1, we are constructing a value here. And we are going to iterate over a hypercube of size of how many rounds in the current stage you have completed. We're going to compute a lag poly for the verifier randomness that we've received in the current stage. And then we're going to multiply it with a range sum over the ox array. So where the partial sums technique comes into play is in this inner loop, instead of having to perform a range sum over the ox array, since we computed these partial sums in one pass of max length stage size, we can actually compute this range sum in constant time, which is a nice trick. Great. So this is the round evaluation, and we've completed the Blendy algorithm. But wait, there's more. Great. So I saved the best for last. This is my favorite optimization to implement as part of the project. If you noticed in slide 13, we're performing Lagrange evaluations. And if you think about it, we're really doing it kind of sequentially. And if you think about it this way, it actually looks a lot like a path in a depth-first traversal. So if we take the multivariate Lagrange polynomial in 0, 1, you can see that it actually maps directly to traversal over a tree. So how does this work? You start at the root with some value like 1. And as you start traversing, as you go down, you multiply this state with whichever randomness you reach. And when you reach a child, you've computed a complete Lagrange polynomial. What else did I want to say about this? Yeah, it's just very nice if you look at it, kind of the key thing to look at is half of the siblings are actually only 1 multiplication and 1 division apart, which is cool. And you actually don't have to do any divisions here if you keep the state in like a queue. So as you're going down, you can push a state onto the queue by multiplying your current state with whatever verifier randomness you come across. And then as you go back up, you can just pop off the queue and you have your state. Great. So a little bit of field operations are reduced with this technique. Yes, and as a recap of what we showed that the Blendy algorithm, the main idea is to divide rounds into case stages. We compute a ox lookup table that's equal to the stage size. We have a partial sums technique, which allows us to compute the inner sum in constant time. And we have this nice technique where we can calculate Lagrange polynomials sequentially. Great. Thank you so much. And there should be some text on this, but I'll fix that later. This is a link to code and also the paper. I can answer any questions, and I can also provide these links if you come see me later.
Any questions? I have a question, as a sort of really zoom out question. Where would I be using your results in? You've heard the different presentations. There's a lot of angles to uses of zero knowledge. Where would this be used?
I think the first thing that comes to mind would be like somewhere where streaming might be necessary. If you have a very large input, this provides a capability that I don't think currently exists. I think it's yet to see if there's really like something super useful you can do with that, but maybe.
Awesome. So very large inputs.
Possibly.
Okay. Just
Related to this, how would you use that? So what is a good K in practice? What do you think K should be?
2 we found is a good K, just because the space usage is very similar to log space, and the concrete running time was most similar to the linear time Sumcheck.
1 second.
Is there a way to make the chunks non-uniform in size, or do they have to be? Because otherwise they're a bit limited as to the case you can choose, right? Like,
Can you rephrase the question, maybe?
yeah. So you showed an example where there are, I guess, 12 variables and 4 chunks of 3 variables each. But do the chunks have to have the same size?
Oh, great question. They do not. No. Yes. So you can see that if you look at the plot of the concrete runtime of Blendy and also the linear time Sumcheck, they get much similar when the chunk size does correspond with your K, but it's not necessary to complete the algorithm. It just adds a little bit of a wonky end, like an end chunk that's not quite right, you know?
I see. Okay. So for example, you said now that 2 is a good, and so it's a good split, right? Half the variables and half the variables.
Yes.
You could do that even if you have an odd number of variables by just.
It'll work. If you have 31 variables, you can still choose K, and then it's just going to do like one. It's going to do a chunk with one thing in it at the end, you know?
Yeah, thanks.
Okay. Round of applause. Thank you very much.
Thanks so much.
Next, we have Giacomo. And I'm hearing that I've seen these slides have a certain template to them.
Yeah. I like the black and
slide wizard.
I like black and white slides. They seem